And what this lesson deals with is transformations of exponential functions. I feel almost as a teacher as though I'm getting bored about talking about transformations of functions. Because what we're going to be looking at today, among other things, is, how do you transform this function f of x equals c to the x? And the fact of the matter is, you know how to transform it. You transform any function by a series of vertical and horizontal stretches and reflections and a series of vertical and horizontal translations. So we're going to be reviewing transformations as it pertains to exponential functions. And then we're also going to be, over the next few lessons, this lesson and the very next one, getting more practice with applying exponential growth and decay as an idea to real-world situations. So to begin with, the warm-up says, describe how the function, I'm going to rewrite it because I don't know how well this is either visible to you or will be visible in the video. We have f of x equals some base, which your textbook, I think, calls c, or your formula sheet calls c. It doesn't matter. F of x equals c to the x is being transformed into a new function, which is a multiplied by c to the x. And I'm going to choose to write the c to the x in brackets just to reinforce to you that the way it's written up here, which is c and then the brackets and then the x, is the same thing. I'm not even going to write this out in words. Well, I'll abbreviate it. We have a vertical stretch by a factor. I'm not going to write it out in words, he says, as he writes it out in words, of the absolute value of a. There is also a vertical reflection if a is negative. This is nothing new. It's absolutely nothing new. I'm just taking a few minutes here to review all of the different things that can happen in terms of stretches and reflections and all of that. Describe how f of x equals c to the x is changed when we go from f of x equals c to the x. There's a little bit of writing here, and I don't mean to go too slow, but I want to make sure that everybody gets a chance to write the stuff down. We're going from f of x equals c to the x to a new function g of x equals c raised to the b times x. This is why I don't like using b for the base. We've got a horizontal stretch by a factor of the reciprocal of the absolute value of b. For goodness sake, on an exam, don't abbreviate your work that much. And then we have a horizontal reflection if b is negative. And again, this is nothing new to you. This isn't earth-shattering. And then number 3 and 4 are reminding us about h and k. But what's actually nice here is, because it's an exponential function, you may not be accustomed to where the h goes. Remember, it's f of x minus h. So it goes from c to the x to c to the x minus h. The x changes to x minus h. Well, it shifts h units to the right if h is a positive number, and it shifts, that's an absolute value symbol, and it shifts h units to the left if h is negative. And I really, again, I believe, I'm giving you a chance to write this down, but I believe that I could probably remove these 4 questions from the lesson and just expect that you know it. But because they're different functions than we're used to, we're actually going through this. What about if we go from f of x or y equals c to the x to a new function g of x, but this time it's c to the x and then minus k. And I'm really spreading out that or plus k. I'm really spreading out that plus k to reinforce the idea that it's an afterthought, it's added afterwards. Well, you have a shift of k units, absolute value of k units up when k is a positive number, and down when k is a negative number. You know, if anything, this just serves as a nice review of what a, b, h, and k are up to when you're talking about functions in general. Any questions with 1 through 4? Okay, so now what we have to do is be able to look at a transformed function, the equation of a transformed function, and identify a, b, h, and k. So we go in this question from f of x equals 3 to the x to a new function that is g of x equals 2 multiplied by 3 raised to the x minus 4. And I could write that as g of x equals 2 multiplied by 3 to the x minus 4 by putting the x minus 4 in brackets with, inside of the brackets with the 3. It doesn't matter. It's not relevant because 3 is a monomial. I would like everybody to take a second here and write the values of a, b, h, and k as they pertain to transformations. And I'll ask some people to be brave and have confidence and type those 4 numbers into the message window followed by comma. So put your a value, comma, b value, comma, h value, comma, k value when you've got them sorted out in your head. I would agree to Aiden, Chloe, Sarah. I think we've got it. We've got this figured out. 2 is the number that you multiply the function by, which is a. So a is 2. There is no b to be seen, but we know from experience that means b is 1. And if you want to be really, really technical, it's this because the b has to be factored out. So when you don't see a b, b is 1. H is clearly 4, and there's no k, and if there is no k, then k is 0. So what are the transformations? I'm going to try to be as efficient today as possible. I'll try. I'm just going to abbreviate all of my answers. Multiplied vertically by a factor of 2. There's a vertical stretch by a factor of 2. And there is a shift of 4 units that away, to the right. There's no horizontal stretch, there's no horizontal reflection, and there's no vertical translation because k is 0 and h is 1. Does anybody have any questions with the answer to this, which is what is in blue? All right, so now we have to graph it. So we are going to start by graphing f of x equals 3 to the x, and then we are going to transform it. And this is a learning exercise. We are not concerned about how precise our graph is or how beautifully drawn our result is. Going back to yesterday, we know that a function like f of x equals 3 to the x has a y-intercept of 1. And every time we go over 1, it's going to triple vertically because the base is 3. You don't need to write this down, and I'm not going to spend a lot of time doing it, but what we're saying is this. We're saying that every time x goes up by 1, you triple y. So when x is 1, y will be 3. When x is 2, y will be 9. When x is 3, y will be 27. Have I got enough room for 4? What's 27 times 3? I think 27 times 3 is 81. and we don't really have enough room to go up to 81. So are we in agreement on those 4 data points, or 4 points? Do you guys agree with that, or is there something wrong? Okay, I'm just checking. My internet might be a little slow in sending out my voice today. So I don't even want to spend time here, you guys, drawing that. Well, I say that and then I'm probably going to draw it. If you want to, you could draw a curve. What we want to do now is take each of those points and apply the transformations to them. So this point that has a y value of 1 is going to be stretched vertically by a factor of 2, which will put it over here at 2, and it's going to be shifted 4 to the right. Now before we go on, the blue graph has an asymptote that's on the x-axis. Can somebody tell me why the new graph will still have an asymptote on the x-axis? Why is it that there's no k value? Exactly, Aiden. The only thing that can move that horizontal asymptote would be a vertical translation. And if k is 0, then that's going to sit there no matter what. Let's move on to the next point. The next point is this one here, which is at 3. So if I double 3, it becomes 6. And then I move it over 1, 2, 3, 4. We could do this with mapping and numbers, but I prefer not to in this lesson. We take a look at the last 2 points. This has a y value of 3. It has a y value of 9. If I double 9 because of the vertical stretch, it becomes 18. And if I move that over 1, 2, 3, 4, this is the location of the new point. And finally, the last point that we had access to Well, thank you very much. That's bizarre. Okay. The last point that we have access to is this one. The y coordinate at that point is, I believe, 27. If I double 27, I think it gives me 54, and then I move 4 to the right. I don't know what that blue dot is there. Oh, you can't see it on yours. So what this graph looks like, and again, don't worry if you're a little shaky in drawing this. That's what it looks like. Any questions with mapping those points out visually from the blue to the red? All right. We are asked for, as well, what do we want? The domain and range. Well, you can take a look at your graph. The domain will be x as any real number. The range will be y is greater than 0 because that's where the asymptote is. There is no x-intercept. The y-intercept can only be found by remembering that a y-intercept is where x equals 0. So we end up with y equals 2 multiplied by 3 to the negative 4. Do me a favor, run that through your calculator and convert it to a fraction for me, and confirm that you get a very tiny number, which is 2 over 81. Good. So the y-intercept, our work is in the top right corner here, is 2/81. This is not really that important in finding. That's not what I want to focus on today, but there you go. Any questions or comments about number 1 or 2 or whatever number this is? All right, number 2, describe the transformations that occur here. Well, there is a vertical reflection. There is a vertical stretch by a factor of 1/2, and both of these things occur because of this A value. A is negative, there's a vertical reflection. A is 1/2, there's a vertical stretch. We also have a B value, if I can squeeze this in, there's the B value of 1/5, and what that means is that there will be a horizontal stretch by a factor of 5, because the horizontal stretch factor is always the reciprocal of B. The number in the equation is B. The reciprocal of that number is the stretch factor. Then we have a K value. There is no H value this time. We have a K value of -5, which means that we shift 5 units down. Whew, red on green. It's pretty wacky on my view. So those are the transformations. Does anybody have any questions with those 3 parameters and what they do? Please, again, we're into the writing phase of this lesson. Please, if you need me to go back, just type so in chat. I'm keeping a close eye on that. So now we want to sketch these 2 functions. Well, again, we start off with y equals 3 to the x, knowing that it has a y-intercept of 1. We go over 1 and it triples, so it becomes 3. On this grid, each vertical square is 2, whoops, and each horizontal square is 2. So we go over 1, which takes us to here, and we triple, which takes us to here. Awkward grid. So that's at 1, 3. I go over another 1 to 2, and I triple 3 to get 9. I go over another 1 to 3, and I triple 9 to get 27, which takes me to here. It's a very awkward scale that I've got on here for both of these. This is from your textbook. So fair warning here, when you're doing questions in the textbook, watch out for goofy scales. So the coordinates of those points from left to right are 0, 1, 1, 3, 2, 9, 3, 27. So now what we need to do is change all of these points. I guess the new graph this time is blue. Last time it might have been red. The first thing we have to do is reflect this point vertically. So it's going to be here. Stretch it vertically by a factor of 1/2. Now it's only down at -1/2. And then I have to shift it down 5. Okay, so I'm going to stop there and talk about the downward shift of 5. If the asymptote of 3 to the x is here, then when I shift everything down 5, eventually the asymptote will be at -5. And this is very difficult to explain long distance, but if you take a look at this point, which is this point after being reflected vertically and stretched by 1/2, that blue point is now 1/2 below the asymptote. And if I take that blue point and shift it down 5, down 2, down 4, down 5, it's going to be 1/2 below that blue asymptote. You might have to get really close to your screen to see that. The next point, I'll make this one a little bigger. The next point is this one. So I need to stretch it vertically by a factor of 1/2, which is going to put it at 1.5. Reflect it vertically, which will put it at -1.5. And then go down 2, 4, 5. But you start to see a pattern here. You start to see a pattern that because of the vertical reflection and then the shift, this graph is going to end up being a curving down kind of situation. We'll take a look at the next one, which is here. It's at 9. Half of 9 is 4.5, which takes us to this point. Reflecting it means it's going to be 4.5 below, which is going to be here, down 2, 4, 5. So negative 4.5 down 5 will be at negative 9.5, which will be about there. And believe me, I'll be honest with you guys. I know that students hate doing this. I'll bet you I hate teaching this kind of thing more than you hate doing it. I think it's a real pain. And I'm not even going to do the fourth point. What we learn is that this graph will look like the following. Roughly. The domain will still be x as any real number. The range is y is less than -5. And there's no x-intercept. And the y-intercept, actually we can read it there. It's 5.5. It's -5.5. We don't need to actually do any algebra. This is not the kind of thing. Oh, was it also stretched horizontally? By a factor of 5. Thank you, Aiden, I missed that. So all those points are going to be stretched horizontally by a factor of 5. Because it's then shifted down 5, it won't matter. I'll show you. And I did screw up there. This point, which is at 1, is going to now be over at 5, and then it's going to be reflected and shifted. But the bottom line is that this point ends up being over here. This point will end up being over here. So all of these points that I've got on the bottom, which are in blue, thank you for that, Aiden, I did forget to stretch horizontally by a factor of 5. They will end up here. So this is what the graph looks like. Thanks for catching that, Aiden. A quick question here. Can somebody tell me why the range is y is less than? What caused the domain, which was y is greater than 0, what caused it to become y is less than a number? Yeah, that's right, Jenna, the vertical reflection. If there was no vertical reflection, then the graph would look, and for goodness sake, don't draw this, but if there was no vertical reflection, the graph would look like this, roughly. But there was a vertical reflection before we shifted it down 4 or 5. All right, hopefully that gives you an idea of how to deal with transformations. Usually the types of questions you're given would be multiple choice, where you're given different graphs and asked to identify the equation. What I'd like you to do is look at your formula sheet, please, for this next little bit of business. On your formula sheet, there is this formula given. And it is an exponential application formula, which is really beautiful for solving exponential growth and decay problems, as long as there is no horizontal or vertical translation. In other words, everybody, when we solve exponential growth and decay problems with this formula, we don't even think of transformations at all. I don't want you looking at this formula and thinking of it as a series of stretches. We're going to use this formula in the first lesson today, in the second lesson today, and it's going to come up later. You need to know in this formula, this is a significant idea, that this and this are not parameters. They are variables. Those two things, y and t, are variables. What we are talking about here are applications where you have something, which we call y, and we track the amount of that thing over time. And if it's exponential growth, it looks like that. And if it's exponential decay, it looks like that. So those two letters, y and t, are variables, but everything else is a parameter. A is a parameter, B is a parameter, and P is a parameter. Please do not think of A and B as having anything to do with stretches. A is the initial amount of the thing, and B is the factor by which things change regularly. We already talked about B, everybody. I would like you to figure out what B would be if a population, I would like you to figure out what B is if a population goes up by 10% regularly. And I would like you to write what the value of B is in decimal form in chat, in the message window. That's 1.1. We already know what B is. I introduced it to you a little bit at a time yesterday. If I told you that we had bacteria, which is doubling, I believe you call that in biology fission. If we had bacteria which was doubling, then B would be 2, because it gets multiplied by 2 regularly. P, and I'm sorry, I apologize on behalf of people who made up these letters. P is the period, which in trigonometry is given the letter K, and K in Unit 1 has to do with vertical translations. So you got to sort this all out. A is the initial amount. It's the y-intercept. We can even make a note here if you're adding to your notes that this is A. So we have y on the vertical axis, t on the horizontal axis, and that's A. So we are going to do, I believe, one example here, dealing with that, and then we will be done with this lesson. So, radioactive element americium, its atomic symbol is AM, is used in household smoke detectors. If you crack open most smoke detectors, there's a little radioactive source in there. If you had access to a Geiger counter, I don't know why you would, but we've got one at the school, and you brought the Geiger counter close to the smoke detector, you would hear a bunch of clicking, and that means radioactive elements are emitting particles. The half-life of the americium-241 is 432 years. So I need to talk to you about what that means, because you're not told on exams necessarily what that means. What it means is every 432 years, A is the symbol for years, 1/2 of the material remains. It gets multiplied by 1/2 every 432 years. And I hope you understand that it doesn't do this. It doesn't start off with a certain amount and keep that amount and keep that amount, and then at 432 years, all of a sudden it all drops. It does so gradually. Well, this is important information, everybody, because this part that I've highlighted, which I'll highlight again, is telling you the value of B is 1/2, and the value of P is 432 years. For some reason, I can't remember discussing P, but on this chart, P is the period of time it takes to happen. Yesterday, every question we did yesterday, it was every year, every year, every year. So yesterday, P was always 1. Well, now it's not 1. P is whatever the period of time is that it takes to happen, which means in this question, P is 432. And by the way, this is the initial amount that you start off with. You can see it up here. So what's the equation? The equation is the amount of radioactive material left is the initial amount times 1/2 raised to sorry, I'm smartboard challenge today, I guess. 200, the initial amount, times 1/2 raised to the t over 432. And now you could use that formula to answer questions like how much is left after 100 years? Or how many years will it take for there to be 30 milligrams or micrograms or whatever that is? And I am sure that you are going to have questions about assigned problems dealing, that's our answer, dealing with this formula. Because I can't give you every type of question. Sooner or later you're going to have to, and this is a goal in high school math, take something you do know and apply it to something you've never seen before. Any questions with coming up with that equation, everybody? All right, so again, we do want to do another lesson today. Here's the assignment dealing with transformations. I think when you get to questions like 9, 11, and 12, those start to be application problems. You don't have to graph anything when you're asked to, and you know what? You don't even have to do every question. Really want to reinforce here in these weird times and this weird situation we're in, you want to look at questions that you think you know how to do and just confirm it, but then you want to move on. You don't need to do every question. Let's take 15 minutes to work on these. That's not enough time to complete them all, but you know the drill. At the end of the day, you're going to have homework from this lesson and the next.